I'm still checking to go to the endpoint. So now we're going to add, not quite there, 49.99 milliliters. Okay, you can almost guess how it's going to go out, but let me go through the mathematics with you. So again, the acid is 10th molar, 50 milliliters of it. The base is 10th molar. Berg wants you to add 49.99 milliliters. Taking dilution into account, the total volume is about 100 milliliters. So the diluted concentration of the acid is 0.05 molar. The base is 0.04999 molar. Okay, it's the limiting chemical, so direct that from both sides. So no base, and the excess acid is 0.00001 molar. In scientific notation, that's 110 to the minus 5. The pH is 5. Okay, I can't stand any longer. We now have to go to the endpoint. Okay, so let's get the pH at the endpoint. Okay, so again, the net equation is hydrogen plus hydroxide gives us water. Okay, we have 10th molar acid, 50 milliliters of it. 10th molar base, we decided earlier that 50 milliliters was the amount needed for the endpoint. The dilution factor is 50 over 100 for both, and notice their concentration is diluted at 0.05 molar. This is a very, very important point, because if you think you're at the endpoint, the concentrations have to be the same. I've seen some complicated problems where they're not exactly the same, round them off to make them the same. If you're at the endpoint, they got to be the same. Now notice what's going to happen in that case, okay? Who's the excess chemical? Neither of them. They both get used up. So after completion step, there's no hydrogen, no hydroxide, and water is formed, but we never use the water. Okay, so here's a case we're going to have to do a change step. Okay, so the change step is we can't have these zeros in the completion step, so now the system is going to go to the right. So we're going to lose minus X of water, plus X of hydrogen, and plus X hydroxide. So at equilibrium, we're going to have X for the acid, X for the hydrogen, X for hydroxide. So we're going to have to solve for X to get the pH. So remember, the K for the reaction is 10 to the plus 14. The mass action expression is used a 1 for the water and X for the other two. Okay, X squared is 1 over 10 to the 14th, rearranging the algebra, which is 10 to the minus 14. Take the square root. Aha, X, which is the hydrogen concentration, 10 to the minus 7. So the pH at the end point is 7. Okay, let's go back to completing the titration curve. So I want to hear some rustling of paper as you guys go to your titration curve and add a pH of 7 at the end point. Let's see, so I've got to put in a pH of 5 on mine. So I want you to notice that the pH is going crazy at the end point here. And I won't bother writing the 7 because you can see that the chart has got a pH of 7. Okay, now I want to do 2 more points with you to get the overall shape on this thing. I want to go beyond the endpoint. I want to go to a pH of 50. Taking dilution into account, 50 and 51 is 101, but we're trying to get the shape of this thing, so just use about 100 milliliters as the total volume. So in the case of the acid, 50 over 100 times 0.1, so 0.05 molar is its diluted concentration. Notice the base, 0.051 molar. Okay. Now, the completion step for a change, now the acid's the limiting chemical, so all of it gets used up. So after the completion step, there's 0 hydrogen ions, but notice there's going to be some excess hydroxide. Now notice that blue line, that means you don't have to go any farther the completion step. We're going to base the pH on the excess base. So read it right into scientific notation. The hydroxide concentration is 1 times 10 to the minus 3. Minus the log of that would be 3. That's the pOH. Subtracted 14, the pH is 11. Okay, now one more point. Let's get double the endpoint. Okay, so notice the situation is the same on the acid. It's 10th molar, 50 milliliters of it. The base is 10th molar in the burette. The Berg wants you to add now 100 milliliters of it. Total volume is 100 plus 50, 150. So look at the dilution factor in both cases. Okay, so in the case of the acid, the diluted concentration would be 50 over 150, which is 1/3. 1/3 of 0.1 is 0.033, and 2/3 for the hydroxide, 0.066. Okay, so in the complete doing titrations, he did titrations the whole summer. As you might imagine, the first 5 were really fun. The last 1,000 were torture. I'd like to show you now how a titration can be automated. Okay, now I once taught a course called Instrumental Analysis, and the student's assignment was to build an automatic pH titrator. Now here's what I gave them. Okay, they started off with 50 milliliters of hydrochloric acid of unknown molarity. Their goal was to figure out how to get the molarity of the HCl automatically. Okay, they were also given 10th molar sodium hydroxide in a burette. I also gave them a pH meter hooked up to a chart. So the chart would plot then pH versus time. Now here was the hard part of the experiment. The students had to calibrate the burette so it delivered exactly the same volume per second. So let's say, for example, that they were able to set this thing up so it delivered 1 milliliter of sodium hydroxide per second. Okay? Now, once they adjusted this, they could let the sodium hydroxide dribble into the hydrochloric acid, and they could go get a cup of coffee, and they could come back later, and here's what the titration would look like. Okay, this is what the graph would look like. Now notice the key thing. Notice you can tell where the endpoint is because that's where you get this steep change. Okay? Now, some recorders actually have the ability to give the first derivative. And notice the first derivative is even better. You can actually tell where the endpoint is even better here. Now, I'm going to take you through the mathematics of the problem. Don't worry about it. I probably would ask this on exam. I just want to show you how it could be calculated because it's pretty cool. Okay, so taking the fact that it took 200 seconds for the endpoint to show up and the burette is delivering 1 milliliter per second. Notice you multiply these together, you find out 200 milliliters sodium hydroxide is needed to reach the endpoint. Okay, then you can use the titration equation. Molarity of acid times volume of acid is equal to molarity of base times volume of base. Okay, so the goal is to solve for the molarity of the acid. Algebraically, then it's going to be molarity of base, volume of base divided by volume of the acid. So sticking to the numbers, okay, it was 10th molar in base. We found out it takes 200 milliliters to reach the endpoint, and you are given 50 milliliters of acid. We find out that the base is actually 0.4 molar. Now you can imagine an industry then, let's say you could have 100 of these machines, they're all putting out the recorder paper. You could do something else, you could go home, come back the next evening, and it's easy to spot the endpoint. So that's the cool thing. The fact that the endpoint is so drastic, okay, makes it very, very valuable in chemistry. Okay, and you guys use the same thing. How did you know when the endpoint occurred when you did this laboratory? You got a color change in phenolphthalein. And why does it change colors? Because the pH changes so drastically at the endpoint. So it's really a wonderful thing that this actually happens in chemistry. This problem goes like this. Okay, calculate the pH. If you're going to mix 45 milliliters of 0.5 molar hydrochloric acid with 40 milliliters of 0.3 molar sodium hydroxide. Okay, let me kind of talk you through the setup on this. Okay, you know hydrochloric acid is strong acid, so you can write hydrogen ions. Sodium hydroxide is strong base, so you can write plus hydroxide gives you water. Okay, then you want to write down the original concentration of HCl 0.25 molar, original concentration of hydroxide 0.3 molar, but you must take dilution into account. So what would be the dilution factor for the acid? 45 divided by 90, right? So 45/90 is the dilution factor there. What about the hydroxide? Its dilution factor would be 40 divided by 85. So you want to find out their diluted concentrations. Okay, that would be the start step. Okay, then you want to do a completion step. You want to do the acid-base reaction. One's going to be excess, one's going to be limiting. Okay, then when you find out the excess acid or base, you can base the pH on the excess hydrogen or hydroxide. Obviously, if you look at the answer, there must be some excess base. So therefore, you're going to get the excess hydroxide, get the POH, and therefore calculate a pH. Okay, so here would be a typical exam question, Berg exam question. So see if you work out the mathematics on this and get an answer of 11.96. If it doesn't work for you, okay, I'll see you tomorrow for office hours. Okay, now, here's something that's always bothered me. I showed you the shape of the titration curve. It changes like crazy at the end point. It's always bothered me. Why does it have that shape? I mean, I understand the mathematics, but is there some way of explaining why it has that particular shape? I'd like to show you the Berg explanation. Okay, now here's what I decided to do. Here was my analogy. I thought of the hydrogen ions as being like marbles. And think of the hydroxide you're added as removing the marbles. So here was my idea. I decided I would pretend like I had 15 marbles, and I didn't remove any yet, okay? And then what I would do is I would start to remove the marbles. So halfway through the titration, you have 25 marbles left, and 25 have been removed. Really close to the end point, I have 1 marble left, and I have 49 removed, okay? So what you're doing when you plot pH on the left-hand side, that's like the marbles that are left. And the bottom one is where it says marbles removed. That's like adding the hydroxide. So I'm kind of disappointed the way my chart turned out, though, because look what it is. At the beginning, I had 50 marbles and none are removed. Halfway through the titration, I have half the marbles left. That's 25 and 25 removed. Okay. And what bothered me is I got a straight line graph. That doesn't look like a titration curve at all. Now, finally, if you can tell me what my mistake is, okay, the marbles left are like the hydrogen ions. Are you plotting hydrogen ions left in a titration curve? No, you're plotting not hydrogen ions, but you're plotting pH. What is pH? pH is minus the log of the hydrogen ions. Therefore, look back at the table here. I decided to take the minus the log of the marbles left. So minus the log of 50 is minus 0.7, 25 is 0.14. Okay, now this explains a lot because notice that the pH doesn't change very much at the beginning because the minus log of 25 and 0, 25 and 0, 25 and 50 are almost the same. Notice the pH is not changing much at the beginning because the logs are almost the same. So when you get a change in logs, look at these numbers here, okay? The log, minus log of 1 is 0, minus log of 0.1 is 1, minus log of 0.01 is 2. Notice how the numbers are changing like crazy because the logs change like crazy, and that's why we get tremendous change at the end of the titration. So why does the pH curve have the shape it does? Because pH is a log scale, and the logs are changing like crazy. So again, nothing I'll test you on, but at least it gives me some satisfaction to explain why the titration curve has the shape it does. It's because of the fact it's a log scale. Okay, homework assignment. So here's some problems from the book. Okay, and so if you can do these, plus the ones I've assigned during the lecture, you would be actually in very good shape. Okay, I hope your brains are full at this point because I have no more for you today. So preview of coming attractions. So on Thursday, we're going to look at the harder titration curve, which is a weak acid versus strong base. And the super challenge, we're also going to look at a titration curve of a polyprotic acid. Okay, but I figure that's enough for today's lecture. Okay, any questions? Hopefully it didn't go too fast for you. Hopefully you're going to take notes on this, and I'm hoping it helps to have those sheets in front of you.